Hello everyone, welcome to this video on classical mechanics. In the previous videos, we have seen that what are generalized coordinates. These coordinates, what are these? The coordinates which would specify the given configuration of the system and they are independent of each other. Then we have defined the degree of freedom for a system of n particles. And then we have talked about the configuration space. Thereafter, we came to Lagrangian approach for equations of motion, and we also told that how this approach, this is better than the existing Newton's approach to define the motion. And this Lagrangian L, which is a function of qj dot and time, that is a scalar quantity, and it does not involve vectors and forces as such. Next, we talked about ignorable coordinates. These are the coordinates which are also cyclic coordinates, and when you take the derivative of the corresponding Lagrangian with respect to some coordinate, say qj, then it would come out to be 0. So this was the definition for ignorable coordinate. And moreover, in the last video, we also saw that del L by del qj dot is equal to pj, and del L by del qj is equal to pj dot, where what is this pj? This is the associated momentum for the jth particle. So this we have defined in the previous video, right? So now, building on this, if the corresponding coordinate representing displacement, that is cyclic, in that case our linear momentum is conserved. That means if we have a system and we are providing a translation to it, then it has no effect on the motion of that overall system. That means the system remains invariant under translation. In that case, our linear momentum would remain conserved. That is the property for this ignorable coordinate. Another property is that if we are rotating some system about any axis, then that rotational coordinate also does not show any effect on the motion. In that case, we can call that as ignorable or cyclic coordinate, and in that case, the angular momentum, the corresponding angular momentum, that will remain conserved, because this momentum is only affected by the rotation of the system. So next we shall also talk about the conservation of energy, and consequently we will see what is Jacobi identity. So let us get started. Here we are making few assumptions. First one is that our system is conservative. That means this L, that depends only on qj's and time, right, and not on qj dot. That means del L by del qj dot, that would be equal to 0, because our system is conservative. And the constraints involved, they also do not contain time, and the Lagrangian, that is only the function of qj and qj dot, right? So this is the definition. Now let us define, let us take the derivative of this Lagrangian. So taking the derivative, because now this is a function of q1, q2 up to qn, and correspondingly it is also a function of q1 dot, q2 dot up to qn dot, right, where these are the generalized coordinates and these are the generalized velocities. So now you are to take the complete derivative of this Lagrangian with respect to time. That means we are to take the partial derivative of L with respect to all of these n coordinates. That means del L by del qj, and then thereafter these are all functions of time. So thereafter we have to perform their derivatives with respect to time. So this is what we have done, and this thing has been done for each of n particles. So we will have terms like del L by del q1 into del q1 by del t, plus del L by del q2 into del d q2 by dt, and so on. These are for these generalized coordinates, and similarly we'll perform the derivative using these n generalized velocities as here. So now look at this term. Here this term is this one, because we can utilize the relations given over here, right? So this is this, and accordingly, and we have these two relations, right? So one should remember these relations. These are really important. So here what we are using, we are converting del L by del Qj is equal to Pj dot. So that is Pj dot, this one. And then you can write Pj as derivative of Pj. And what is Pj? Pj is again, using this relation, it is equal to del L by del Qj dot. So we obtain at the end del L by del Qj, that is equivalent to ddt of del L by del Qj dot. So we'll substitute this value over here. So let us see what do we get. We have del L by del T as such, summation as such. The value of this would now become ddt of del L by del Qj dot. So this term, and then we can write this term as the derivative of Qj. That means we have written it as Qj dot now, and the second term as such. So now can we club this term? Yes, we can club this whole term as the product of del L by del Qj into Qj dot and taking its derivative. So when you apply the differentiation on this term, so you will take the derivative of first term, keeping the second as such, like here, and then you'll keep the first term as such and take the derivative of second, so you will obtain this term. So ultimately our terms, we have dl by dt as such, and then you can write this term as summation as such, d by dt as such. This term is what? This is our Pj. So this is Pj and Qj dot. Why Pj? Because of this earlier relation. This is Pj, and so we obtain from here ddt, we can move the terms to the right hand side, so we obtain this term, right? Now derivative of some quantity is 0, that means the quantity itself is a constant. So this constant is known as the constant of motion, and let us call that by j. This j is the constant of motion, and this identity over here, this is known as the Jacobi's identity. And moreover, if the given qj's, they are functions of pj's, in that case we call this j to be h, and that h is known as Hamiltonian. So basically our Hamiltonian, this becomes simply summation Pj Qj dot minus L, and this is also equal to which is a constant. So here we have defined the Hamiltonian. One should remember what a Hamiltonian is, and you should also remember what the assumption, what are the assumptions that we made during deriving this identity. So we have assumed that our system is conservative, constraints do not involve time, and the Lagrangian is a function of Qj and Qj dot only. So this is what we have assumed. So this is our Hamiltonian. Next, in the previous video we have talked about Hamiltonian, and we have also talked that this Hamiltonian is a operator which is based on this set, basis set Qj and Pj, where Qj's are the generalized coordinates and these Pj's, they are the generalized momentums, right? Momenta. These are the generalized momenta. So these h, that is depending on this Qj and Pj, and then we have this term as such minus L. L is also a function of Qj and Qj dot and not T. So this is the identity that you should note. So here there is a term which says this h, sometimes it is known as the constant of motion, and sometimes this h is known to represent the total energy of the system. So now in some cases this is the case, and in some cases this is the case. So this h is a constant of motion when it does not involve time, and it is the total energy when the coordinate transformation, that means previously you have r1 as your coordinates, now you have converted your coordinates to q1, q2 up to these, the generalized coordinates. So this transformation does not contain time explicitly. That means these ri's, they do not depend on time as such. So this thing is not this thing should not be there. But these q1, q2, qn, they obviously depend on time. So that is why we say this coordinate transformation should not contain time explicitly. In that case, the Hamiltonian, that represents the total energy of the system. So moreover, in the last video we have compared our approach, Lagrangian approach, with that of Hamiltonian's approach. So let us also make few more remarks regarding this. So here in the Lagrangian approach, we had used the basis set Qj, Qj dot and T, whereas in Hamiltonian, our basis set becomes Qj, Pj and T, where these Qj's, they are the generalized coordinates, Qj dot, they were the generalized velocities, and these Pj's, they are the generalized momentas. And this T represents time. So here independent coordinates were only Qj's and time. And because these Qj dot, they were depending on Qj's. And here in this case, the independent coordinates, they are Qj's and Pj's and time. So all of these are independent coordinates. Moreover, for n particle system, our path is represented by 3 n dimensions. If you have remembered, we have shown this through various figures in the previous videos, whereas here it includes 6 dimensions. Why? Because in the first case we only had q1, q2 up to qn independent coordinates, right? And for each n particles we had 3 dimensions. So that is why overall we got 3n dimensions, whereas in this case we have n position coordinates, that means 3n position coordinates according to 3 dimension, and we had n momentum coordinates, that means 3n momentum coordinates in 3 dimensions. So overall we had 6n dimensions to represent this system. The space corresponding to the Lagrangian, that is known as configuration space, and we have already studied about this, whereas the space corresponding to Hamiltonian, that represents the phase space. So this is the definition over here of phase space, right? So in the phase space, actually what we are doing, we are saying there is only one possible path in phase space for a system of particle. Why? Because here you have 6n dimensions, so 6 initial values are provided to solve the system, whereas here for a point we had infinite number of possible paths. Why was this the case? Because initially we only had 3 values which could define the system. So here in configuration space, the system is not completely defined using these 3n coordinates, whereas in phase space we can completely define the state of any system. So all in all, in phase space, the advantage of using this phase space is that there is less arbitrariness about the path and comparing to the configuration space. Moreover, we can also say that the path given in phase space, that is the actual path which the particle follow. So it gives you the complete information about some particle moving or the system of particles moving in the space. So that is it for this video. Thank you for watching.